take over. That new topic um, is slope deflection methods that we're going to discuss today. Continue from the force methods that we have discussed last week. So let's recapture what we have done recently. So I think, as you know, we done the force methods last week. I think the force methods was the introduction of solving the beam and truss problems, which are specifically indeterminate structures. Now, indeterminate structures are the structures uh, which has a uh, which has a degree of indeterminacy, so which has some extra forces that you wants to you have to identify. For examples, in the mechanics of solid and previous weeks, we have this kind of a problems. Well, let's say load is P, length is L by 2 on each end. On this kind of a cases where you have a three reaction force typically required to calculate. Well, it is easy because you have some of the moment equal to 0, some of the force in the x direction equal to 0, some of the force in the y direction equal to 0. So these structures need to be in equilibrium, meaning that this structure is not in the space. All the forces and all the moments coming on that particular beam is 0. And using that conditions, we can calculate those three unknown reaction forces. Basically, they're saying that if you have a three unknown forces and three equilibrium equations, mathematically it is possible for us to calculate those unknown forces. What's quite easy, and we done many examples on that ones. Now, more recently, what we have introduced to you, saying that now you are expert on that ones. Let me put something more challenge on your plates. Let's say similar beams. This is fixed at one end. This is fixed at one end, and the pin at another end. So when you have fixed, you have. Let me put this on as a rollers. So more and you have three reaction here, and you have one more reaction here, So here you can say total 4 reaction forces, and you have total 3 equilibrium equations. In that case, you have one extra force that's are remaining. That is the degree of indeterminacy. We call it static degree of indeterminacy. We can give them name static degree of indeterminacy. Now that is an extra quantity that you want to find. So for that, we introduce the compatibility conditions. If you remember that the deflections, we remove that supports and make this one as a primary structures, and then we also put this deflection and this deflection equal to this deflection. That is the compatibility condition. And from that compatibility conditions, we find these unknown forces that we are targeting to find. There was a very simple equations that I introduced to you. I think if you remember that one last week, and if you start solving the assignment questions, it will make more sense to you that you can find the static degree of indeterminacy. Now the static degree of indeterminacy here you can see is a static degree of indeterminacy of the beam and truss. For the beam, you have 3m plus r, which is m stands for the members, how many members you got, how many reaction force that you got, and how many joints. N is standing for how many joints you got. And for truss, very similar equations, which equal to m plus r minus 2m. M stand for the member, how many members you got in the truss, what is the reaction for, how many reaction force you got, and how many joints you have, that is the n. So basically this one they talk about how many unknown forces you have, how many unknown forces, and this one how many total equilibrium equations, total static equilibrium equations. Similarly here, these first three first these terms is representing unknown forces, and these terms represent a number of static equilibrium equations. So basically let's talk about how many unknown forces, take away how many equilibrium equations you have in the systems. And probably you remember these kind of an examples that we solve as well, that someone asked you to find draw the shear force diagram and bending moment diagrams. That you can solve by drawing the primary member first, and then find a displacement for the primary members, and then you can draw another primary members. Primary members, by the way, the determinant structures, so you can use the virtual work methods to solve these displacements. You can use the table. That tables also will be useful for standard cases. If it is not a standard case, you can use the virtual work method to solve these displacements. So that, by the way, you need to calculate two displacements. Once you calculate those two displacements, if you make those two displacement equal to, you can find the unknown force. And once you find this unknown force, you can use the three equilibrium equation to find another three equilibrium equation, three unknown forces. Similarly, truss problem similar. You can remove one of the redundant, which is your members, and from there you can solve that truss problems as well. All right, so let's we are reaching at the very end of your semesters, which is a good news at one hand, that you are finishing one subject from your course, and I think we are progressing good so far. Students are learning many good skills and knowledge. Students are getting confidence to solving the examples and so on. As we progress more advanced topics, the previous topics are making more sense because these topics are built on your skills. You remember that, right? We did not straight away in the week number 1, we did not straight away introduce these topics. We go all the way to the semester 1, and we spend almost 4 weeks to refresh your memory. Refresh your memory, meaning that if you don't know these topics, basically we are not be able to progress on those ones. So we make your foundation very, very strong by running the quiz, by putting some assignment questions, and running a lot of lecture examples, workshop examples, and we make very strong foundations that's built from your mechanics of solid knowledge. Some of the things that you already know, some of the things we introduce, and so on. And then we also done some new topic which are not super complex, but they are quite little bit challenging than these ones, but you can handle those things. And then we done the virtual work methods where you have determinant structures, and then you find a displacement for that. There is a double integration methods that you can use to find the displacements as well. Now in the force methods, last week we discussed that ones. So the force method has one limitations, that it can work very well when the degree of indeterminacy d equal to 1, static degree of d equal to 1. And if it is becoming greater than 1, and if it is 3, it is quite challenging to solve those, to apply those force methods. So now we are starting to introduce the displacement methods. So this is the force methods. Now we are introducing the displacement method. Displacement methods. Within these displacement methods, the first methods for this displacement method is the slope deflection method. So there is a big group of the methods that falls in the displacement methods and the force methods. The force methods we already finished that ones, but now from these weeks we are starting the displacement methods. In the displacement methods, the subcategory is the slope deflection methods. Moment distribution methods next week also part of the displacement methods, and the stiffness methods in the following week, in the week number 11, is also part of the displacement method. Displacement methods is also used to solve the indeterminate structures. It's also used to solve for indeterminate structures. It can use for determinant structures as well, but I think you don't need it. But because you can use the static equilibrium to solve this indeterminate structure. And so those methods again used for indeterminate structures, but they are more powerful than the force methods. How? I'm going to tell you. Now, after finish these slope deflection methods, you can take question 3 from your assignments. You should finish question 1 and question 2 by this time. If you have not started your assignments, I'm start worrying about you because they are long and lengthy. So every week I suggest you to put at least 2-3 hours to finish those questions, right? These subjects require to spend at least 10 weeks or about 8 weeks every week from your. This is not the extra workload that I'm putting on your. It is just a 15 credit point subject. So probably 4 hours with us, another 2-3 hours by yourself, and then 7 hours or something, right? So it's not quite intense subjects every week. If you do these examples by yourself, you are soonly finishing your assignments. And it's an open book. You can use internet, Google, YouTube, these lecture notes, recording, and all to solve that assignment questions. We are here also to help you to answer your questions. So you can ask our questions via email. We can have Microsoft Team meetings during the workshop. You can chat with us, and we can help you to progress on your assignment. So don't fall behind. Just start working on your assignments. Now, this week's, as I mentioned, we are start introducing the lectures for the slope deflection methods. Now, these slope deflection methods are quite old, almost 109 years old by these names, and it is first developed in 1914. And bit of history for that, I think. Um, George Manny has introduced. I think he's a German academic staff who has introduced that, George Manny, and it's 1940s. Very quite old methods, but still we use it, very fundamentals to understand. At that times, for at least for 10 years, a lot of engineers use these methods. Then moment distribution methods comes into the play after 10 years. Then people start using these methods. Uh, we may, I think when you go to industry, you may not use these ones, but I think there is very fundamentals and foundation methods that will help to understand many concepts for the structure analysis. So therefore we are teaching these ones, quite old, but still we teach these methods, and it's quite useful as well. You can use it. No one going to stop it if you want to use it, but it's quite lengthy. So that's for therefore it's requires some attention. If you need more information, you can use our library to see our books, and in the chapter 11 you can find these methods details in this our recommended books. But if you attend my lectures and workshops, and if you go through the lecture notes, you are pretty set to go for these methods. But if you are keen to get some extra informations, you are happy to collect from this chapter 11. Now, today's lectures is we're going to introduce the slope deflection equations. I will give you some analysis procedures, step-by-step procedures. We solve a couple of examples, and we finally summarize our lectures in 2 hours times. Okay, let's do the slope deflection equations. Now, what is slope deflection equations? The definition is given. So let me read word by word, and I will put more details there. The slope deflection equation is a general of a general beam under the external load P. That's, let's say, external concentric load P, uniformly distributed load W, and support settlement delta. So let's say this support is settled by delta, is the equation to describe the relationship between the internal end moments with the slope theta and deflection. So it is a relationship between the internal moments with the slope and internal moments with the displacement. So is m equal to something times theta, or m equal to something times delta. So this kind of a relationship between the moments, by the way, that moment is the internal moments. I hope now by these times you know what is internal moments. So you have done the plenty examples on these kind of things. So internal moments with the slope, that is the slope deflection equation. Internal moments and displacements, that's again the slope deflection equation. So if someone asks what is a slope deflection equation, the slope deflection equation is basically the equations or the relationship between the internal moments and the slopes and the internal moments and the displacements. So don't worry about these figures. I will explain you these figures in a great detail, so you will understand where these equations will be used and what is the usefulness of these equations. Now, last week we done the similar things, which is the static degree of indeterminacy. You remember this one, right? Static degree of indeterminacy, DS, which is 3m plus r minus 3m. Now, I like to introduce the new terminology, which is kinematic degree of indeterminacy. Now, what is kinematic degree of indeterminacy? It's referring the number of possible motions in a structure that can be determining using the equation of static equilibrium equation. So, for example, if you take any structures, let's say if you take a structures, and let's say this is pin support and load is applied, what is the possible displacement? So this point here, it is fixed. So it cannot go X or Y, it cannot go Y, it cannot go in the Y direction, it cannot rotate. So there is a zero motion. These points cannot go left or right, cannot go up and down, cannot rotate. But if I come back to this point, these points again cannot go left or right horizontally, it cannot go up and down vertically, but it can rotate. So there is a possibility that these points can go rotation at 1. So this is represent a kinematic degree of indeterminacy. What is a kinematic degree of indeterminacy? If you look at the whole structures and see, if I say kinematic degree of indeterminacy for this structure is equal to 1, it means that in your brain or in your thoughts back of your head, you can imagine the picture saying that these structures, this whole beam or frame or something, that structure is will have a somewhere somehow one displacements. It could be horizontal displacement, it could be vertical displacement, or it could be rotation. So that is the possibility of that structures to have that kind of a free degree of freedom. So these are the fixed degree of freedoms. You can say this zero, meaning that these points cannot go left, right, cannot go up and down, cannot rotate. But this particular point, which is the pin support, it has a one free degree of freedom. So we can say that this is a one kinematic degree of indeterminacy. I hope it is makes sense. Um, um, then how do you, it is a measure of the complexity of structures, geometry and connectivity. I already explained that. The kinematic degree of indeterminacy is calculated by subtracting the number of independent equilibrium static equilibrium. So how many equilibrium equations minus total number of unknown displacements. So that is the definitions. So total equilibrium equations minus total number of unknown displacements. So that's the definition of the static indeterminacy. Let's take an examples, because that is the definitions. Definitions sometimes does not make sense until we apply that methods into our actual things. So let's consider the beam PQ that is here. At P is PQ fixed at P, so that is fixed at here, and is a pin at Q, subject to a load F, that load F as shown in the figures, determining the static and kinematic degree of indeterminacy. Now, static degree of indeterminacy, last week you done it, right? I want you to not learn the kinematic degree of indeterminacy independent of static. I want you to have a feeling of what we done in the last week as well. So it will be the revision for you. So static equilibrium equations, if you remember that, right? 3m plus r minus 3n. If you go back to our force methods, you can find these equations. How many members you got? 3 times 1 members. How many reaction forces? 1, 2, 3, and 4 and 5 reaction forces. So 5 minus 3 times how many joints? You got 2 joints. So 6 plus 5 minus 9. Oh, sorry, minus 6. So I think 11 minus 6. Am I doing something wrong? 3 number of joints is 2, 3, 1 members. How many reaction force? 5 reaction force minus minus 3 times number of joint is 2. So sorry, this is not 6, but this would be 3. So yep, so 3 plus 5. Thank you very much. 3 plus 5 is 8. 8 minus 6 equal to 2. So that is the 2 extra forces that we need to find. So that is, you remember last week, right? That's similar kind of things we done it. So that is a kind of revision. But that is the static degree of indeterminacy is used in the force methods to calculate the unknown, represent how many unknown forces that you have to calculate. That is, say that this structure is statically indeterminate by degree 2, right? So there are, what does 2 meaning? Static indeterminate. In back of your head, you can imagine that this structure has a 2 unknown forces that I need to solve on top of your 3 equilibrium equations. Now, this week I'm introducing the new terminology, which is kinematic degree of indeterminacy, DK. Now the equation, I just put it there for you all to understand. 3j minus r, which is j is number of joint. By the way, that is the same thing that we put the definitions. Say that how many equilibrium equations. So that is that many equilibrium equations and how many unknown displacements that you have. So in this case, you have 3 times 2. which is how many joints you got. You got 2 joints, so 3 times 2, 2 joints. And how many total unknown displacements? So if you have, I think that is total unknown forces. I just check it. So in that case, you have 1, 2, and 3 reaction, 4 and 5 reactions. So 6 minus 5 equal to 1. Right. So this one, what is this represents? That one represents saying that that many, that one represent that if I do this displacement curve like this points is fixed. So it cannot go X or Y, cannot have any displacement here. All the displacement 0 here, rotation 0. But at this particular point, if I take it, this point can rotate theta. Right? So that is the one represent that these structures has a one possibility of going going to the rotations, right? That is by 1 degree of freedom. You can see the difference. The static equilibrium is 2, but kinematic indeterminacy is 1. Does it make sense, kind of? Or I can stop here. Static thumbs up. Let's test your knowledge. Okay, let's do the truss one. For the truss one, you remember that, right? 3m plus r minus 3n, which is how many members? You get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11 members. So 11 plus how many reactions? Pin has a 2 reactions, roller has a 1 reactions. So 3 reactions times 2. How many joints? Joint 1, 2, 3, 4, 5, 6, and 7 joints. 7 joints. So 14 take away 14, 0. So static equilibrium is 0. You can see that there are 3 unknown reaction force, and then you can find those 3 forces, and all these internal forces are also be calculated. So that's all good. So it's a degree. So 0 meaning it is a determinant structures. For static equilibrium, it is determinant structures. But kinematic degree of indeterminacy, if you want to calculate, so 2j minus r, which where 2 is number of j is number of joints. You know how many joints? 7 already. So 7. So 14 take away 3 is 11. So you have total 11 kinematic degree of indeterminacy. What does it 11 represent? I don't want you to just find it. You just want to feel it. The 11 meaning that these points can have a displacement in the x and y. Right? So this is 1 and 2. This displacement can go it as well, 3 and 4. This one as well, 5 and 6, 7 and 8, 9 and 10, and there is a one more 11 here. So you can see that 11 numbers represent there are total 11 unknown displacements that in the system that is you can find there are total 11. So that's the representation of kinematic degree of indeterminacy. Static degree of indeterminacy represents how many unknown forces you got more than equilibrium equations. This one kinematic degree of indeterminacy represent how many displacements that you got in the possible displacements in the systems. Now you all raise your thumbs up. So can you all please solve this one for me? What is the static degree of indeterminacy and what is kinematic degree of indeterminacy? Equations, by the way, given on the top if you want to use it. But if you understand the story, can you please put your answer in the chat or say it by unmuting? You have a couple of minutes to test your knowledge. Before we moving on to the next levels, I want to test your knowledge that this concept is clear in back of your head. I don't want you to remember anything, by the way. I don't ask you to remember any equations. Equations already on the screens. When you solve the assignments, the equation would be there. I just want you to understand what is the meaning. If someone say that this is a static equilibrium by 1, what does it mean? If someone said this is the kinematic degree of indeterminacy by these numbers, what does it mean? I want you to feel that numbers, that if I see these numbers, it means this. All right, let's try. So first one, degree of indeterminacy would be 3. How many members you got? 3. How many members you got? You got 2 members. Plus, how many reaction force? 1, 2, 3, 4, 5, 6, and 7. 7 reaction forces. 6 plus 7, 13. Take away 3 times how many joints? 1, 2, and 3 joints. So 13 take away 9 equal to 4. Now 3 times how many joints you got? 3 joints. How many reaction force you got? 9, take away 3, 4, 7. So equal to 2. So two two kinematic degree of indeterminacy. So these 4 represent that there are total 4 unknown forces. As you can see, they are 3, and this one you need to find. So that's 4 extra forces. This one too, because there is, I think this particular joint has a rotations. You can see there is a rotation at here and there is a rotation here. So there are 2 rotations that you need to you need to find. So therefore, there is a kinematic degree of indeterminacy of 2. So I hope you guys understand. You don't need to find these numbers, by the way. You need to feel that numbers, what that numbers represents in the structures. Those number 4 represent that you have 4 extra forces more than the equilibrium equations. And those 2 represent there are 2 unknown displacements. Can you solve these ones as well? Static equilibrium and kinematic degree of indeterminacy. DS, so 3 times how many members you got? 2 plus how many reaction force? 1, 2, 3, 4, and 5. 5. So total 6 plus 5 equal to 11. And then minus 3 times how many joints? 3 joints. So 11 minus 9 equal to 2. Correct? So there are 2 extra forces more than the equilibrium equations that we can't solve. So that is number 2. So that is number 2. Kinematic degree of indeterminacy. We can solve by say that how many joints we got? 1, 2, and 3. How many reaction force? 1, 2, 3, 4, and 5. 5. So 9 minus 5 equal to 4. So you can see there are 4 kinematic degree of indeterminacy. Probably it will goes here 1, 2, and then 3 and 4. That's we are trying to find. Similarly here, I think it's look like this one as well. So I think you can do it all this one by yourself. There is nothing, but I hope you understand this. So I hope you understand that. All right, so that's all good. Now, you understand the static equilibrium equations, kinematic degree of indeterminacies, all are clear for you. There is nothing super complicated, and you understand the meaning for that one as well. So let's take an one simple beam, that typical beam which has all the complexity, like all the loads and all kind of settlements and everything, and we'd like to develop the slope deflection equations. Now, what is these beams? Let's start with the first figures. Let me explain you that first figures. Now, these figures that you are seeing is part of, let's say, whole beams. Let's say someone putting this beam and someone has rollers here and someone put this loading on these ones and someone put the P load and so on. So someone try to, if I cut this beam and just take this beam, part of the beam here, right? So this is just, you can see this is kind of a cut here, right? So it means that something is continuous here, something is continuous here. So it is just something in the middle of one big beams, right? So I hope it is understand that is the portion of your beam. So something like a small part cutting from the whole beams, where each has a UDL load W, it has a concentric load P, it has a settlement. This portion that supported B is settled by delta. It has these chord rotations. That's chord rotation is psi. It has this friction moment, deflection curves, and everything's are there. Now the question is, we like to develop the moment displacement equations, like slope deflection equation for this beam. This beam meaning that these equations that we're going to develop, that will going to be useful for. So we like to develop the general equations, and that equations we can use it for any cases. So we need one slope deflection equations that will be useful to calculate the internal moments. Right. So, and you remember that slope deflection equation is the relationship between the internal moments with the slope and displacements. So that's the definition. Now we're going to use the superposition methods to calculate those kind of problems. Now let's take saying that you remember that, okay, this problems is we always tends to make the structures determinant. You remember that in the force methods, what we done when we see the indeterminate structures, we somehow make it primary structures which are determinant. You remember that, right? What we done, we said, okay, you have one unknown forces. We remove that unknown forces from the systems and we make it primary structures. You remember that one, right? From the last week. Similarly, we can do the same thing here, that when we see the kinematically indeterminate structures, so kinematically indeterminate structures meaning you can have theta A is one of the kinematic degree of indeterminacy. Theta B is also kinematically degree of indeterminacy. There is a settlement. If it is unknown, then you have a settlement here as well. And there would be some kind of a code rotations that is developed due to the this one. So there are three different kinematic indeterminacy, which is theta A, theta B, and there is a code rotation psi. So there are three different kinematically indeterminacy. Now, as you know, in the force methods, we also done the similar that, okay, when you find the static equilibrium equation equal to 1, then we make it primary structures by removing that one force. And we say now these structures is statically determinant. And now we use our conventional methods. We can do the same thing here. What does it same meaning? That what if I remove all these members to this one? Let's say all these kinematic indeterminacy remove. Can you please tell me what is the kinematic degree of indeterminacy for these ones? And the equations for these ones would be 3j minus r. 3j minus r. Can you please tell me kinematic indeterminacy of the structure here? 3j minus r is the kinematic degree of indeterminacy. So can you please tell me what is the degree of kinematic degree of indeterminacy? You put the thumbs up, right? Saying that I understand the kinematic degree. People move on, and that is enough. So I want your answers, because if you don't understand the previous step, there is no point to move forward, because otherwise it's quite challenging for us to go and find to understand the concept. So what is the kinematic degree of indeterminacy for this structure here? By the way, those two ends are fixed. These are fixed at A, fixed at B. The kinematic degree of indeterminacy for this structure here. So do you agree that this kinematic degree of indeterminacy would be 3 times joint is 2 minus reaction force is 1, 2, and 3. 1, 2, and 3. That is a 6. So that is 6 minus 6. So that is 0. So you have 0 kinematic degree of indeterminacy. So you can see that if it is 0 kinematic degree of indeterminacy, meaning that structure is determinant, right? So what I want from here to here, I make it the structure first kinematically determinant. Initially was kinematically indeterminate by the degree 3. You can see theta A, theta B, and psi. So what I done, I come here and put two big clamp meaning the holders. I go in the beam, put the clamp and make that one as a fix. So when I make this clamp, then it become the kinematically determinant structures. Now this displacement methods does not like that the force is coming on to that members. This displacement methods does not like it. If you have this one, let's say like this, sorry. If you have like this, let's say A, B, and C, there is no force in the B to C. So AB, they don't like it. They are not happy. BA, BC, they are happy because there is no loading coming on to the members. They are happy if the loads coming on to the joints. They are happy when the loads are at least on the joints. That is the displacements method. That's the nature of the methods. So that saying that if you have a load on to the members, let's say any loads coming on to the members, that's That's, let's say, someone walking on the beams and someone standing in the middle of the beam and so on, then this method does not like it. It's completely not like it. It says that I don't like it. So we have a solution for that. What we do it, we calculate the fixed and moments. We have equations to calculate the fixed and moments to transfer all these forces to that respective joints. So that's we solve these problems. So first problems, we clamp it, we arrest all the joints to make it fix, to make it kinematically determinant structures, to make it kinematic indeterminacy equal to 0. That is our first job. Everyone understand that? We go there somehow, bang, we put the nail, we put the hammers, and then we say that this joint don't rotate, don't displace. We fix it. We go plates and we just weld it, or we do the clamping and all, we fix it. Okay, that is job number 1. We just fix it, kinematic indeterminacy, make it 0. Then the next job is to go and find the fixed and moments in the whole beam where you want to transfer all your internal forces to the joints. Everything you put the clamps, at that same clamp you want to throw all the forces to that clamp. So that's another another step. So I hope everyone understands so far. Now, now all these ones so far so good. Now, but in the reality, those are not clamp. In the reality, these are not clamp. So they say that, okay, don't worry if they are not clamp. What we going to do it? Let's release one of the clamp. Let's release one of the clamp and get the theta A to release. Right, so let's make it 1 degree of indeterminacy to allow, kinematic degree of indeterminacy to allow. So can you please tell me the kinematic degree of indeterminacy for these ones? You tell me kinematic dk equal to 0 here. So that's all good. And the dk for this structure is 3. Now, can you please tell me the kinematic degree of indeterminacy for these ones? Kinematic degree of indeterminacy for these ones. And by the way, the equations for kinematic degree of 3j minus r. 3j minus r. So can you please tell me, you tell me dk equal to 0 here, and I explain you the story as well. Now, can you please tell me the kinematic degree of indeterminacy for that second one? That is theta A. That one is saying that theta A is allowed. So total 3 degree of freedom. So dk kinematic degree of indeterminacy 1 here, which is the theta A. So what we done? Somehow someone go there and remove 1 or 2 nails and remove that plates. That's removing the plates allow that point A to rotate theta A. Immediately when you rotate theta A, you need the moments to rotate this theta A. Let's say, let's forget about that is theta A. Let's say someone wants to rotate that joint by degree 1. Let's say you need rotations because theta A is quite complex. So let's say you have a questions here for you saying that you have a fix here, you have a roller here, you have a roller here, and someone try to rotate by 1. How much moment do you think is required to rotate your joint number A by degree 1, like rotation 1? If the length of the beam is L, Young modulus of the material is E, and moment of inertia I, so amount of moment required to rotate that joint A is 4 EI on L. Where is coming from? It is like if you know the force method, it is indeterminate structures, and you can use your force methods to calculate this M value, which is 4 EI on L. What is that value? That is the 4 EI on L value. Amount of moment, you need 4 times the Young modulus, the materials that you are using, the geometry, the moment of inertia, and the length of the beam. That much moment do you require to cause 1 degree rotation in at point number A. If there is a 1 degree of rotations required is 4 EI on L, how much moment is required for theta A? So just multiply by theta A. So that's theta A, the moments that you can see here, that moments required to cause the theta A rotation is 4 EI on L theta A. What is the reaction moment here? That would be the half of what you are getting here, right? You can see that. You can do the calculations here, by the way. That will help you to find that 2 EI on L theta A. So that is the reaction force. So if someone applying the moment 4 EI on L theta A, then the another end the reaction moments, because there is a reaction moments here, that is 2 EI on L theta A. Oops, sorry. So now again we go back and put this nail or the plate back and say that theta A is 0 again. Then we go back and remove something from the B side and say that okay, theta B is allowed. You can go. So that is again degree of kinematic, degree of kinematic, degree of kinematic indeterminacy equal to 1 here for these structures, which is theta B. Now, same structures, amount of moment required to cause the unit rotations 1, which is 4 EI on L, and it is an elastic region, so times by theta B. So the amount of moment required to cause the theta B is 4 EI on L theta B. So that is the 4 EI on theta B moment. So that's all good. Second one done. And again, this side is just the reaction, which is half of that. So you can calculate the reactions. Now the third one is this settlement. So that will create these chord rotations. So how much moment do you require to create this unit settlement? That is 6 EI on L square and then times by delta. And then similarly, it is a fixed both ends. So same reaction moments because in equilibrium. So we have same reactions created here. Now, I did not put those forces, the real forces here, because we already put this one. So if I superposition all of this one, if I add all of them, I will get the real structures. Do you agree with me? Because degree of kinematic degree of integration is 1 here, degree of kinematic 1 here, equal to 1 here. So our total all 3 add up 3. All real loads here. Right, so everything, if you superposition these ones, I can get my real structures, which has a kinematic degree of indeterminacy equal to 3, which has a real loadings, and by doing these 3 or 4 steps, I am able to transfer all the loads add to the joints, and I'm also able to find those fixed and moments. So you with me, if you understand that once, then we can say that moment MAB, by the way, this is the internal moments, and AB stand for the near node and far node, which I'm going to explain you in a minute. So if I want to calculate the moment MAB, I can have this one plus this one plus this one plus this ones. You with me? Because superpositions, if what is the moment, internal moment at this particular point would be the addition of all these 4 components, because it's a superposition. So that's all good. I plus them all. Substitute the value 4 EI on theta A, 2 EI on theta B. This one going this side's opposite to this one, so therefore we put minus and then fix and moments AB. And similarly, you can do the same thing for other side. MBA 2 EI plus theta A, 2 EI theta A, 4 EI theta B, 4 EI theta B, minus this is opposite moments, so 6 EI on L square, and fix and moments. Right, so there are 2 equations we can write in the general form, right? Let's say AB meaning that this is near node and this is far nodes, right? AB near far, or BA. So if you have moment near far, so this is near node here and far node here. This is near node, far node. So if I take out 2 EI on L here, so if I take the 2 from here, EI gone, L gone, so here you have 2. So 2 theta N, and A is the near node, and 2 EIL common. This one completely gone, and B is a far node, so theta B. Minus 3, this EI gone, L gone, and the 6 out of 6, 2, so 3. And this one is your span rotations, which is delta on L, so we put psi, plus fix and moments. Same thing here, by the way. Same thing here. If you take the 2 EI on L out, 2 EI and L out, you have a 2. This is the near node. B is a near node. So you can see this is near node to 2 near node plus this is far node. So this is far node minus 3. This gone. So only 3 left, 3 and span rotations plus friction moment. So this is the equation. If you don't understand any of these ones, don't worry. We will not ask you to derive these equations. This is the takeaway message from the whole another 15 minutes of discussion. These equations that you want to use it all the times. This is the equation. So this is a summary. That these equations, if you have it, and this equation is called slope deflection equation, relationship between the internal moment, slope, and displacements, because that's span rotation has psi has a delta on L. So this is called internal, this is called slope deflection equations. Definition of slope deflection equation is the relationship between the internal moments and slope and displacements, right? Where E is a Young modulus, I is a moment of inertia, L is the span rotations, near node, far nodes, and this is the span rotations. By the way, when your pin or roller without a concentric moment, so if you have this pin or if your far nodes, like for examples, let's say you have this, and this, then this, and you have these problems like this, and two here, let's say A, B, C, and D, and A, B, and C, and D. So let's say these problems here, CD. So in that case, CD, so D, you don't allow to fix these ones. You can't go and clamp that far and fix. OK, you don't allow all the internals, you can fix it. All the internals you can go and hammers and sew and put the plates and arrest all these ones, and you can make it kinematic indeterminate structure. But the end, very end, you can't do it. OK, so for that case, there is a different equations that you can use when your far node or pin, far node is pin or roller. So that case you can use these equations, which we're going to take it in the examples. So now different, you remember all the way from week number 1 to week number 8, anti-clockwise is positive. That's what we use so far. In our subjects, we use anti-clockwise is positive because there is a right hand thumb rule in from the physics that's saying that we have these hands are our fingers, and these thumbs are going in the directions which is your thumb rules, right hand thumb rules. So therefore anti-clockwise is positive. That's moment is your finger, which is goes anti-clockwise when you thumbs goes up. Now from week number 9 to week number 11, which is 9, 10, 3 weeks, we are going to use this convention where clockwise is so anti-clockwise is positive here from week, and from week 9 to week 11 clockwise is positive. Someone might say it's quite confusing because you are now trying to say that all these methods previously we learned anti-clockwise positive, and how do we remember that in the exam or in the assignments that okay, this one positive, this one is quite confusing. You can put this note somewhere saying that anti-clockwise from week 1 to week 8, those topics are clockwise, and I put the details as well. Moment and rotation are positive when act clockwise on the span and vice versa. In the displacement method, clockwise moment is taken as positive because moments are used to find the deformation in the structures. As I said, in the displacement methods, displacement is your unknown. Force method, force is your unknown. So in the displacement, your moment taken positive because moments are used to calculate the displacements. Moments are not used to calculate those forces. These moments are specifically used to calculate the deformations like a displacement. When a clockwise moment is applied to a beam or structure, it causes top structure to compress. It's like this smiley face, and bottom to stretch. It's a tension. So these deformation are calculated as a positive quantity in the displacement method. Hence, the clockwise moment is also considered positive. So that's the reasons that it creates the smiley face in the displacement methods. Therefore, it is positive. These are some of the equations for slope deflection, friction moments. I'm going to show you how to use those in a minute. Analysis procedures. When I take an examples, probably it will be more clear for you. Yeah, so when you have these ones, you can you can make it you can convert into these kind of structures. So let's take an examples. Any questions by the right? Does it comes here week 9? No, it did not come. Let me see if I can. Okay. All right. So being with the far fixed. So our question here is to find the reaction forces. Our question is find reaction forces. We need to find the reaction forces. That's our questions. Look at this highly undetermined structures. You have AY, you have AX, you have moment A, you have BY, you have CY, CX, and moment C. How many? 1, 2, 3, 4, 5, 6, 7. So total 7 unknown forces. 7 unknown forces. And then you have some equilibrium equations. So highly undetermined structures like a degree of static indeterminacy equal to look like 4. Right. So if you use force methods, of course you can use force methods, but I think it will have a 4 compatibility equations and it will be huge job for you. Probably by hand is not possible to solve this one. So this times this slope deflection method step in, regardless of how many degree of indeterminacy you have. This George Manny, the name is George Manny. He come up with these smart methods saying that regardless of your force methods that you are using, it will be quite challenging, but these ones we can do it. So step number 1, let's calculate fixed end moments. Let's calculate fixed end moments. Let's calculate the fixed end moments. Now to calculate the fixed end moments, we can draw up the pictures here. So this one A is fixed. We make it B is a fix as well. You can see the internal ones. You remember the theory for the clamp. So we make it B is a fix and fix end moments at AB here and fix end moments at B. And you know this theory saying that we don't want any forces coming on to the members. And for BCs, let's say fix the B and let's do the C here. And you have this loading, which is 6 kilonewton per meters, and the length is 6 meters here, 8 meters. So the fixed end moments here is fixed end moments for this one is BC and fixed end moment for CB. So here fixed end moments for AB equal to 0. Fixed end moments for BA equal to 0 because there is no any forces that is coming here. So therefore it is 0. In this case, fixed end moment for BC. Now we can go back to our lecture notes and get these tables from where is the tables? Here you go. These tables going to be useful. Let's get these tables. And you can use these tables in your assignments or in the final exams. You no need to remember. Again, you no need to remember these tables. So edit, copy. And let's take this one to over here. All right, so here we can find a similar one. So similar one look like this ones. I think this would be, we need to switch this one because you can see these ones look like similar, both side fixed, and these sides long sides, because you can see our problem is like this. Our problem is like this. B and C and 6 kilonewton per meter, and then you have 6 meters. Length is 6 meters. So you happy with me to write saying that let me see. So you're happy with me to write fixed end moments at so this end would be like this, and this N would be fixed end moments of BC. Fixed end moments of BC, and that would be your this ones WL square on 30, right? So that is WL square on 30. You can see this point is small, this point is matching here, and this one is WL square fixed end moments of BC equal to WL square on 20. Now let's go back and check it. Fixed end moments of BC, and that BC we are having these ones BC. We would have a minus because that is which side is going this side, and that is your anti-clockwise. So you can see at the start you can say that clockwise is positive. Clockwise is positive, right? You remember that, right? That in our displacement method, all clockwise are positive. So this is anti-clockwise, so that is minus, and that BC equation was WL square on 30. WL square on 30 minus 6 kilonewton per meter times length is 6 meters square over 30. So that will give me value of minus 7.2 kilonewton meters. I hope it is understand. Fixed end moments of CB, and that is clockwise moment, so positive, and the CB has an equation of WL square on 20. WL square on 20, 6 kilonewton per meter times by 6 meters square over 20, you get 10.8 kilonewton meters. So step number 1, fix and mount. Simple. So what you do, you take all your beams, break it down. Just break it. AB, take the AB, make it all internal fix and calculate the fix and moments. That is the step number 1. All your displacement methods, you calculate the fix and moment. Very simple. Table will be given to you. From these tables, you identify the equivalent, identify the close match, and then you calculate the fix and moment. So that is the step number 1 that you always do these ones. Step number 2, you write the slope deflection equation. Slope deflection equations. Now you have 2 equations for the slope deflections. One that is these ones. Let me get these equations. One is these equations. We have 2 slope deflection equation only, so there are 2 options. One that I'm just taking it from our lecture notes, by the way. And there is a second one, that's this slope deflection equations. This is another one. Now, how do we use these 2 different equations? So when you look at our questions, we need to look at the far node. Far node meaning extreme nodes. Extreme nodes that you can see here. These extreme nodes are C is a fixed supports. So this one is a fixed supports, which is C. Always look at the right side one, far one. If it is fixed, meaning that you need to forget about these ones. You can't use this one. So by the way, these ones, when you have this kind of structures, you can use this one. If you have a structures which is this, and for this last part, you can use this equation. I will show you one examples where we use these equations. Now for these ones, for our case, we forget about this one, but this is just for explanations. So here, let's take the member AB first. Member AB first. So I can write member moment AB equal to 2 EI on L. AB, I'm just writing it for here. 2 near node is A because A plus far node is B, theta B. 3, this is theta on LAB because that psi is is a rotation and fixed and moments of AB. I hope you understand that. I just used expand that ones. So 2 EI, length of AB. Length of AB was 8 meters. You can see. So that is 8 meters. 2 theta A is 0. You can see kinematic indeterminacy. You say that theta A is fixed, so there is no rotation at A. So theta A is 0. Theta B, there is a rotation because you already calculate kinematic degree of indeterminacy. You remember that. So theta B, we have unknown value. -3. There is no any settlement. So that displacement is 0. Length is 8 meters. And the fixed end moments for AB is 0 that we calculate. So we substitute these ones equal to 2 and 8 cancels. So that makes it EI over 4. That is 0 theta B. So that is theta B. So that's your equation for MAB. Similarly, we can do other side MBA, because you can see from the figures that we have two figures. Let me put this one here that we calculated. We just need this one only. Let's get this one. Yep, we just get this one. Okay, so that's all good. Now, so here we just got MAB. Now, similarly, we're going to get MBA. Let's get the MBA. Now, this times I can write the same, I can use the same equations. Let me put this equation here as well. Let me get this equation down here. There you go. So let me write it MBA 2 EI on LBA plus 2. Now theta B is your near node. Far node is theta A. 3 delta on LBA plus fixed end moment of BA. So 2 EI, length is 8 meters for BA. Theta B we need to find. Theta A was 0 because fixed supports. There is no settlement. So 3 times 0 on length 8 meters plus fixed end moment is 0. So this cancels 4. So EI on 4, 2 theta B, and these are all 0. Again cancels. So 2. So EI on 2 theta B. So that is your MBA. Right. So this is a member AB done. Now we can do the same procedure for member BC. Your head saying that it could be half, but requires some attentions. Right. Okay. MBC. Let me write it. 2 EI on length BC. 2 near node B theta C. 3 delta on L BC plus fixed end moment of BC. Right. So now we can get these figures down here as well. So we can see it, what is happened with our things. Okay, so 2 EI on length BC is 6 meters. So 6 meters. 2 theta B we need to find. Theta C is 0, fixed supports. No settlement. Length BC is 6 meters. Fixed end moments we found before. Minus 7.2 kilonewton meters. Minus 7.2 kilonewton meters. So that is the fixed end moments. Now we can quickly sort this out. So this one cancel, this one cancel, 3. So 2 EI because this is 2. on 3 theta b. This one gets 0, this one gets 0, minus 7.2 kilonewton meters. So this is MBC. We can do the similar. MCB equal to 2 EI on length LCB 2 theta C plus theta B. It become your style afterwards, solving some example with me to do. Every member has these two internal moments. So you can calculate those two moments. So 2 EI on length BC was 6 meters, 2 theta C and theta B is 0. This one 0. This is length CB, which is 6 meters, plus friction moments of CB is 10.8 kilonewtons, 10.8 kilonewton meters. So we got this one cancels 3 meters. So we got 2 theta C on 3. What happens here? Oh, theta C would be 0 here. So this will be 0. So 2 times 0 and theta B would be your case. So we would have a EI on 3 and theta B plus 10.8 kilonewton meters. So that is the second step that we're going to use the equilibrium equation. So step number 1, we all find friction moments. We take member AB, find a friction moment, take member BC, find a friction moments, and so on. Then we do the slope deflection equations. We take it again, member AB, find the slope deflection equation. Then take member BC, then find the slope deflection equation, and so on. Solve the answer. Now, step number 3, we're going to use the equilibrium equation of moments at node B. So we're going to use equilibrium equations of moments. So moment equilibrium at node number B. Why we choose node number B? Because at that node we have equilibrium, because you can see a kinematic indeterminacy. You remember that, right? So node number B, that's the one that we make it unstable. So we make it fixed and so on. So we need to make sure that all the moments, some of the moments at this particular point, because you can see you have MAB and you have MBA. You have MBC and you have MCB, right? So at this particular moments, at this particular joint, B should be in the, so sum of the moment at B equal to 0. So MBA plus MBC equal to 0. So MBA we already calculated. MBA was EI on 2 theta B. Let's substitute that. EI on 2 theta B. Plus MBC, we got it, which is 2 EI on 3 theta B, 2 EI on 3 theta B minus 7.2 equal to 0. So we can do the lowest common denominator. So 3 EI theta B on 6 plus 4 EI on 3 theta B equal to 7.2, and that is 6. And that would be 7 EI theta B equal to 7.2 times 6. So 43.2, and theta B equal to 7 EI. So theta B equal to 6.17 over EI. So that is your unknown variables. You remember that is the kinematic degree of indeterminacy. That's the displacements that you don't know. Now, once you find the theta B, we're going to substitute that, and then let's do the fourth steps. Step number 4, we're going to find the n moments. Once you find these rotations. Now to find the n moments, we can go back and take the equations. MAB was EI on 4 theta B. MAB was EI on 4 theta B. So EI on 4 theta B was 6.17 on EI. So EI was cancelled. 6.17 over 4, 1.54 kilonewton meters. MBA, let's get the equation MBA. EI on 2 theta B. EI on 2 theta B. So EI on 2 theta B was 6.17 over EI. EI cancels 6.17 over 2. We got 3.09 kilonewton meters. MBC, let's get MBC. Here 2 EI on 3 theta B minus 7.2. 2 EI on 3 theta B minus 7.2. So 2 EI on 3 times by 6.17 over EI minus 7.2. This cancel. So you get minus 3.09 kilonewton meters. And MCB equal to MCB, we got this ones. EI on 3 theta B. EI on 3 theta B plus 10.8 equal to EI on 3 times by 6.17 over EI. EI cancel plus 10.8 equal to 0 equal to 12.86 kilonewton meters. Now stop here and look at these numbers. You remember that equilibrium at B? You remember that equilibrium at B? It's proven here that you should get equal answer like 3.09, but opposite minus. One of this is minus. So stop here. And when you apply the equilibrium equations, make sure that you get the same answer with the plus and minus. If you did not get it, something is wrong. So stop sign here. I don't want you to just close your eyes and keep doing it all these ones without verification. This is one of the verifications. This is the verifications that is making sure that your calculation is going on the right path or not before moving on to the next steps. This is all good. Now, so in that case, I can say that these values that I can put it on my figures on my questions. That question is supposed to be copy and we can put it here. So in that case, I can say 1.54 is MAB and the positive, meaning that is clockwise. So 1.54 kilonewton meters, MAB positive. So MAB, let me write MAB. Okay, give me a minute. Give me a minute. All right, so now 1.54 clockwise. Then we have 3.09 positive. So it's clockwise. So that is clockwise. This is clockwise and MBA 3.09 kilonewton meters. Then you have this anti-clockwise. So that's anti-clockwise goes here, MBC. MBC going to be anti-clockwise and that MBC equal to 3.09 kilonewton meters. And then MCB, that would be clockwise. And that is MCB equal to 12.86 kilonewton meters. So now I hope you understand that. Now, once you know these details, then you can calculate the reaction force easily. How you can find the reaction force? So you can get the AB out. You can put the reaction force AY, BY, and then you have a moment at AB and this one moment at BA. So now if I know this one is 1.54 kilonewton meters, that's we already calculated. This one's I know 3.09 kilonewton meters. This is point A, point B. I can do sum of the moment at point A equal to 0. Let's put the clockwise positive here because we done the clockwise positive. This will goes clockwise, so 3.09 kilonewton meters clockwise. This one also clockwise, which is clockwise 1.54 kilonewton meters, and this one create anti-clockwise moment. So By times this length we got is 8 meters. 8 meters. So By times 8 meters equal to 0. So By we're gonna get it is 3.09 plus 1.54 divided by 8. You got 0.58. Then if you do some of the force in the y directions, AY going up plus BY going up equal to 0. AY plus 0.58 equal to 0. So AY equal to minus 0.58. This one done. You can do these ones. Here, 1 BY. So this is left side, let's say this is right side. And then CY, the moment going this side like this. Which is 3.09 kilonewton meters. That is anti-clockwise, negative was there. And this is clockwise, and this one is 12.86 kilonewton meters. And you have loading of 6 kilonewton per meters, and that was 6 meters. Similarly, we can do some of the moment, let's say B and C. Some of the moment at B equal to 0. Let's say clockwise positive. So this one minus 3.09 kilonewton meters anti-clockwise plus 12.86 kilonewton meters these moments. Then CY minus CY times 6 meters. And probably this one would be your 1/2 times 6 times 6. So 36 over to 18 kilonewtons. That's in the middles. And I think I remember that 2/3 and 1/3. So 2 divided by 3. 2 divided by 3 times 6 give you 4 meters and then 2 meters here. So this one 18 kilonewtons and that will create the clockwise moment. So plus 18 kilonewtons times by that 2/3 is 6 meters equal to 0. So let me minus 3.09 plus 12.86 plus 18 times 6. You got these ones divided by 6. So CY equal to something is did not goes right. CY equal to 19.62 kilonewtons. Let me fix up something. I think something I need to fix up 12.86 and 3.09. 09, and that would be your 0.5 times 6 times 6, which would be 18. That's all good. And that would be centroid, 2/3 and 1/3. So 2 divided by 3 times 6, which is 4 meters and 2 meters. So if you apply the moment here, 18 would be clockwise and then minus 3.09 and plus 12.86, and then you got CY, which is anti-clockwise. So CY times 6 meters plus 18 kilonewtons going here times by 6 meters. So let me go the centroid of the triangles. It's right there. I think something that is not matching, but anyway, that's all good. So 3.09. Let me put in my calendar again, plus 12.86. Then plus 18 times 6, 117. That goes across, divide by 6, give you 19.62. Anyway, that's all good. So BYR going up plus CY also going up, which is 19.62 kilonewtons, and then coming down minus 18 kilonewtons equal to 0. So BYR equal to 19.62 minus 18. So 1.62, bring it across, minus 1.62 kilonewtons. So BY, that would be BY left side. So we need to plus that one to get these ones. BYL, I think there is something I mix up, otherwise it would work. Minus 1.62. That's not going to match. So I think something is. I will fix up and I think I will let you know. I think the answer is there, but I think somewhere I just screwed up something. But that would be 0.58 minus 1.62, so minus 1.04 kilonewtons. So somewhere I think I can fix it later, but I hope you get the overall details. So if I put the reaction forces on the figures, copy and paste. So reaction forces, this reaction force we already got from the moment, 1.54. So going this way, 1.54 kilonewton meters, the reaction moment. This force here, which is coming down, but I think that is coming up. But anyway, that's not an issue. AY is coming down 0.58 kilonewtons. And there is a moment here, which we going to get it 12.86. 12.86 kilonewtons. So this is all the reaction forces that we calculated. All right. Any questions? Any suggestions there? I will straight away write on these ones because I don't want you to waste your. I think there are a couple of examples that we go through it. In the past, students put the comment saying that there are not enough example to follow. Therefore, we add more examples, but they are quite similar. Only difference is these ones, that if you have far end is roller, then what you're going to do it. I think perfectly same steps. What you do, you calculate the friction moment first. You clamp these ones, member AB. Use our tables. There you go, tables is here. This figure is match. WL square on 12, WL square on 12, both side. So you put WL square on 12. You put the negative because this is anti-clockwise, this is clockwise. So this is positive. You can see this is clockwise is positive. So 120 is positive, WL square, 40 is coming from here. And the length is coming from here, 12, 1 minus 120. Calculating friction moment is quite simple. Go in the tables, find the fix. So first of all, you can just fix all the internal joints fix. You don't need to fix the end one. Okay, you can't fix these ones. That's bad one. So you can't fix the C, but you can fix B, and you can find the friction moments at AB. Here you can find the friction moment for BA, and then you use these slope deflection equations. You remember that slope deflection equations for that. Slope deflection equation. Here you go. Oh, these one standard equations that we use, slope deflection equations that you can use. And you can plug the values and you might get these values. Okay, so by the way, theta A equal to 0, theta B, that's we need to calculate. Theta C, we don't need to calculate. So theta B, we need to calculate, and theta A equal to 0. So whenever you see theta A, you put 0 and keep it theta B. Simple. Now this this portion is fixed, but you can't fix this C. Therefore, you remember that we have a second slope deflection equations that we can use. We can first calculate the fixed end moment for BC. You can go back into this, go back here and fix end moment for BC. I think this 3PL on 16, that looks perfect. 3PL on 60, the another side is roller, this side is fixed, and we have 3PL all 16. Yeah, 3PL all 16. These ones we put it negative because it's anti-clockwise. Clockwise is positive. So that's therefore we put these ones and minus 22.5 kilonewton fixed end moment. Now these times you can't use this slope deflection equation. You remember that we are using this slope deflection equations. This slope deflection equations when your far end is fixed. When your far end is fixed, but in here your far end is roller or pin. You can see your far end is pin or rollers. This one is fixed, but you might say that this one also roller, why you make it fixed? But all internal are fixed. Far end, this ones you can't make it fixed. So in that case your far end is roller. So for that case we can use these equations, very small equation, simple, same style. You have fixed end moments, you have theta b, and you have this psi. So you have this theta b, and these others are 0. So MBC, there is no MCB, by the way, because this one, the moment here at this point is 0, right? Because when it's fixed, only you have a reaction moments, otherwise there is no moment. Then you can use the equilibrium MBA, which is MBA and MBC equal to 0. Substitute the value, you calculate MBA and MBC, and you find the unknown rotation theta b. Once you find the unknown rotation theta b, you calculate MAB, MBA, and MBC by substituting back. You have theta b, you substitute back here in these equations. You substitute back in these equations, and you substitute back in these equations to calculate the end moments. So you can calculate this MAB, MBA, and MBC. And then you can just simply use these ones and find out this reaction force using those end moments. You can also take these ones and calculate the reaction forces. That's reaction forces are there. Okay, when you have a settlement, 80 millimeters, same thing. You can see these settlements are overhand section can be converted into concentric moments. So we're going to convert these ones into the concentric moments, and we're going to use the settlement. So what we're going to use, that this part here, 8 kilonewtons times 3. So this is 8 times 3, 24. So this problem become like this. These problems become like this. A, and we just remove this guy by putting the moment here, 24 kilonewton meters. Simple. So these whole problems is become AB only. We're not going to draw it BC. And like we're not going to calculate end moment for BC and so on and slope deflection equation. Just we remove the whole part of BC, just completely ignore it. But instead of BC, we put this because you can see this is the clockwise moment. This create the clockwise moment. So 24 kilonewton meters, I put it clockwise moment. And this is 4 meters. And this is 24. And this one going to settle by 80 millimeters. So I think when you have a settlements, you need to put these 80 millimeters, that's 0.08 meters, because 80 over 1000, that is 0.08 meters. You remember that last two equations, we are taking this one 0 because delta over L, so delta settlement was 0. But this one here, we have a settlement, so that's 0.08, just additional mathematics that you're going to use. All other details are same. All these fixed end moments calculations and everything are same. Then you can use the equilibrium at point B. You have this point B, MBA and MBC. We got 24. So you remember that 24, and you got theta B. And you can substitute theta B. You calculate these end moments back, and then from that end moments you can find the reaction forces. If you got the concentric moments, that's also like if you have external concentric moments here, you can see there is an external concentric moments and there is a far end fix. So you can't fix this one, but you cannot fix this one, by the way. You cannot fix this one. So for these members, you need to use these another slope deflection equations. So here you go. You can make this one fixed. So that is B. BA. So there is a BA fix and moment BA. There is a tables where you can use there is a tables where you can calculate these 3PL on 16 depending on clockwise or anti-clockwise. You can put positive. This is yeah, in here that is clockwise, right? So that is 3PL on 16. And yeah, there are different EI. So you need to make sure that you substitute that EI, like you have EI, then you replace this EI by 2 EI or 3 EI, depending on the given. So that's I replace. Theta B, theta A is 0 because there is nothing here. There is no settlements here, so 0. So you got this MBA. Similarly, you can make it this one fixed, and these all these are fixed. So fix and moment BC, fix and moment CB and MBC. Now this 12 kilonewton meters comes here. You can see this 12 kilonewton meters. There is an extra 12 kilonewton meters, and that is going clockwise. So MBA plus MBC and minus because clockwise is external moments. Your internal moment clockwise positive, but this one is your external moment. So external moment and clockwise is negative. You remember that, right? And the external clockwise like previous week. So therefore it is minus. And then you calculate theta B. You substitute theta B into our slope deflection equations, and you will be able to find those end moments. Yeah, and then from that end moments, you can find the reaction forces. Similarly, you can convert this 20.20 times 1.5, and you can put this one here. You can see like these guys, we can remove it, and this one we can fix it, finding end moments. These guys we can't fix it, and these guys we can't fix it. And I think that's whole shear force and bending moment diagram, as you can see there. Yeah, for the frame also, there is a quick notations that I can put it. There are two kind of frames, frame without sideways and one with the sideways. What is the difference? That if your frame, like if you push, like if you apply the loads and all your joints are staying at that position, you can see these frames are not swinging, like it's not pushing, the whole structure is not doing this kind of swinging. So that kind of say is a without sideway or restraint frame, because you can see these joints are rotating, but they are staying on that positions. They are just staying at that particular position. It's just rotating, but it's not translating. In here, you can see joint D is completely goes to here. Right? It's just when I apply the load P, because there is no, if I put the restraint, some kind of a restraint here, like some kind of a beam or something strong beam, then this point will not be able to go. Like look at this one, I can put something here, then it cannot go. So if this kind of frame where your frame is going, like it's going sideways or going up and down, those joints, it's called with sideways. Right, or unrestrained frame. There is no restraint. These frames can go left to right. Now this lecture is limited to the no sideways frame only. So we are going to just no sideways frame. So there is no any translation that is happening. Right, so let's say determining the internal bending moment at joint B of the frame, so on in this one, all these are fixed and C is pin. So frame is nothing different than your beams. It's just like you can make it this one fixed, and you can work on this FBC. You can make this one fixed, and you can work on FAB. So you can see member moment AB, moment BA. Oh, sorry. And then because this is pin, so you can't fix it. This is far end is this one, so you can make this one like this one fix, and you grab this one here, calculate the fix and moments, and you can use the slope deflection equations. You can use the equilibrium here, whatever the moments applying on these ones, that can be done, and you can calculate theta B. Substitute theta B in our slope deflection equations, and you can find the end moments. From that end moments, you can find the reaction forces, and you can draw the shear force and bending moment diagrams. Another one, you can look at this. This one you can't fix, but these ones you can fix. You can take this part and calculate the fixed end moments for AB and moments A, BA. Then you can take this part BC and again you calculate those end moments. Then you take this part, again you calculate those end moments and you apply the equilibrium here. You can see that I took this part and make this one point B is fixed, and we did fixed end moments, we calculate end moments. Then we go here and we take this BC. By the way, we can't make this one part, this one is fixed. So we need to use another slope deflection equations. We calculate fixed end moments here, end moments here. And then we take this part here. And again, we calculate MBD. Then we apply the equilibrium equation here at point B. You can see MAB, MBC, MBD, and we substitute and we calculate theta B. We substitute back theta B into our slope deflection equations to calculate the end moments. Once you calculate the end moments, you can calculate the reaction forces that are shown here. So in the summary, I think there are two equations that you always focus on. When your far end, like for examples, you have these kind of structures. For these ones, you can use this one. This one, you can use this one. You can use this one because all internal are fixed. But if you have your far end is pin or roller, for these ones, you can use this one. But for these ones, you can use because these far ends, you can't fix it. So therefore, there are two slope deflection equations that you always use. Not much difference over here. When you have this overhang, like something is hanging like a balcony, you can convert this one into the concentric moment and you can remove this part. Right, so I think that's the overall